I'd like to welcome you to Acromag's webinar on resistance and temperature sensors and applications. Again, thank you for making time out of your day to watch this webinar. My name is Don Lupo. I'm the Director of Sales and Marketing for Acromag's Process and Automation Division. I will be your presenter today. Today's agenda, we're going to be discussing three sensor types, potentiometers and slidewire type sensors, thermistors, and RTDs, or resistance temperature detectors. We grouped these sensors together into one webinar because they're all resistance type sensors, but they have different applications and require a different amplifier or signal conditioner measurement technique for interface. So we thought it'd be good to group them all together and look at the amplifying technique that you need to measure these and make a good measurement. Primary purpose of the webinar is to become familiar with these sensors, their general applications, construction, wiring, and again, most importantly, what are the key things needed in your signal conditioner for a good measurement. Okay, this slide sort of outlines what potentiometer slidewire sensors are. What are they? Well, they are resistance sensors. Basically, they're a fixed resistance with three terminals on them, one at each end, and then a wiper arm in the middle. And so they're kind of a three-terminal resistor, and they're typically, as a three-terminal resistor, they're sensed as a voltage divider where the resistance doesn't change. You're going to provide excitation across the end terminals, and then you're going to measure the voltage pickup on the wiper arm as it slides from one end to the other. There's a really neat picture. It's an early 20th century slidewire type rheostat in the upper left-hand corner. That's a good picture of what I thought was a good graphic on what a slidewire might look like. It's a bunch of coiled wire with terminals at the end and a slider in the middle. Now, you can just wire up to two terminals on your potentiometer, the wiper arm and one end. And if you do that, that's called a rheostat, and that's actually used as a variable resistor. It can also be used for position measurements, but basically that'll be a variable resistance as a sensor. Okay, there's two basic types of potentiometer slidewire sensors. There's a rotary kind, and there's pictures in the middle where you can see a knob on the top where you could put a knob on, and that's called a rotary type potentiometer sensor. You turn it clockwise or counterclockwise. Or there's the linear type, or a slider, or a fader, and that's shown in the bottom. You might see slider or faders, you know, on music soundboards, mixers, or even as a dimmer switch for a light switch. Now, just a little history. Who invented the sensor? Johann Christian Poggendorf invented the potentiometer slidewire in 1841. Okay, some potentiometer slidewire applications. How are they used? Well, in general, this sensor is used for manual control of an analog signal. Manual control of an analog signal, and it's typically sensed as a voltage divider, as I mentioned earlier. It's used for position adjustments, if you're going to adjust a gate or a valve. It's also used for position sensing as feedback, maybe in servo controls. The picture in the middle is an actuator, and that yellow wire coming off, I'm not sure if you can see it, but it says precision linear potentiometer. That's feedback for the position of that actuator. Potentiometers can be used to set speed or motor controls. They can be used for temperature controls or heating. They could be used for audio volume controls. As I said earlier, lighting dimmer switches. They can be used for circuit, you know, gain and bias or attenuators. Or if you use some analog transmitters, they're used for zero span pots on some analog transmitters in the market. We have some. Other kinds of pots could be used for level controls. I know there are magneto-resistive level control products out there, which are basically a bunch of resistors put in series with reed switches in parallel with them, and then a magnetic float switch will go up and down the stem, pulling in the reed switch across a resistor that's in the tree, creating a kind of like a potentiometer measurement, but it's used for level control. That's called magneto-resistive. There's also helixical or collapsible coils that are also used in level controls. It's basically the same principle, though. It's a fixed resistance, and as the liquid or level kind of goes up and down, it collapses the material, shorts out the resistor in one part, and then you can measure the variable resistance as a percentage of span to do level control. So those are some applications for potentiometer slide wires. They're also good for position. There's a string pot up in the upper right-hand corner where they actually, sensors can have a wire that's tied to a spring or a coil that's mechanically tied to a pot. So and you can affix this to your process, so as something moves, it pulls the string out. As the string gets pulled out, it's actually changing the wiper arm on the pot, so you can actually get a direct translation between position and a potentiometer wiper arm output. So that's called a string potentiometer. There's a lot of consumer and industrial applications for pots. At one point in time, many people thought traditional potentiometers would be obsoleted by digital pots and encoders, but there's simple, reliable, and even low-cost applications for traditional potentiometer slide wire sensors. Moving forward. There we go. This slide talks about potentiometer construction. There's about 5 different types. I think the top 3 are the most prevalent, but there's wire wound construction, carbon, ceramic, metallic, combined, it's called CERMET. There's metal film, and then there's a concept of conductive plastic where they embed carbon grains into plastic and create a potentiometer that way. In the upper right-hand corner, not sure if you can see that real well, it's a light blue, but there's a comparison between wire wound, carbon, CERMET, metal film, and conductive plastic. You'll notice that these potentiometer slide wires can range from 10 ohms to 100 k ohms, some up to 10 mega ohms, 5 meg, metal film goes up to 20 k, and conductive plastic can be 4 meg. Most of the pots that we use in the process industry for position or level measurements are in the 1 k to 10 k ohm range, but you can get pots with all different shapes and sizes. They've got different temperature coefficients when you're selecting this sensor, some as low as 50 parts per million if the ambient temperature changes around the sensor, some as high like a molded carbon as 8,000 parts per million. So that resistance is going to change over temperature. Generally, when you have a pot, you want to, if you're doing a 3-wire position measurement, it doesn't matter too much about the variable parts per million. But if you're doing a 2-wire rheostat, then it makes a big deal. Looking at all of the materials here, metal film, even wire wound, and CERMET are all real good types of construction. They've got typically 0.1%, 0.05% resolution, around 0.1% linearity. The metal film has a very good frequency performance. And so, when you're shopping, you're going to want to take these things into consideration. Where is it going to go? You're also going to want to take into consideration, the environment. If there's gases or caustics around, what it might do to the materials in your pot. The picture in the bottom is a very nice graphic. It's a rotary potentiometer. You can see the element. If you look downwards, it says element, where they wind it's called wire wound, but they wind a coil around the shaft, and then they use a precious metal wiper like a platinum alloy to, as you turn the dial, it'll be the wiper arm. And then right off the front it looks like a screw that you can put this, it's a stainless steel shaft, but with that shaft you can put a knob, or that could be customized to mechanically link to your process for a position measurement on a gate or a valve or an actuator. So that's a really good graphic. In the bottom left-hand corner, potentiometers are linear sensors typically. And this graph kind of shows you that it's a linear sensor. It's got a tolerance band to it, plus or minus, but it's a linear output. Now, there are potentiometers that you can wire and coil so that they give you a logarithmic output, and customers might use these in music mixers or sound elements. So you can get nonlinear outputs or logarithmic, but in general, when you're doing position or level measurements, we view potentiometer slide wires as a linear sensor. Let's see. Here we go. One other thing on construction, too, if you're using a slider or fader versus rotary, sliders or faders are not really sealed, so they're conducive to contamination on the pot. So if you're in a process or industrial application, you want to also take care to know if your potentiometer is sealed so it doesn't change the value. All right, this slide talks about measurement technique. Notice the picture up at the top. It's a 3-wire sensor. There's your fixed resistor, and you have 3 terminals, 2 on the end and 1 wiper terminal. And as you turn the wiper arm clockwise or counterclockwise, it will progress towards one end of the terminal or the other. Now, the best measurement for position using a potentiometer is a 3-wire measurement. And what you need for a good measurement is a stable excitation source. And down below, we're showing you a diagram from an Acromag amplifier. I don't know if you can see this, but we use a 0.3 volt excitation. It's not very high. It's current limited, but it's a very stable, very accurate 0.3 volt excitation that goes across the pot. And then, so it's low voltage, and it doesn't pump a lot of current through there, and there's not going to be any worry of self-heating. Excuse me real quick. And then we're sensing the wiper arm into a high input impedance A to D converter. Okay. Now the pot value, when you're using pots specifically for position, you're going to want to use potentiometer values at least 1,000 ohm sensors or greater, maybe 1,000 ohm or 2,000 ohms. And if you do that, then the lead wires leading out to the pot, whatever gauge they are, if they're less than an ohm, you will have very little effect of lead wires on your measurement. And just for example, 20 gauge wire is about 0.01 ohms per foot. 17 gauge wire is about half that, 0.005 ohms per foot. So if you're doing a 3-wire measurement off of a potentiometer slidewire type sensor, you have a good stable excitation source, and your pots are values around 1,000 ohms or 2,000 ohms or greater, you're not going to be worried about lead wire compensation or the effect of lead wire resistance in the measurement at all. Now, the one thing you want to do, though, is keep your pot value. You don't want it to be too high. For example, you don't want it really to be 100K or 200K ohms. You want to keep it below 10K ohms or closer to 1,000 or 2,000 ohms, and that's because there is a source impedance value. The Thevenin source impedance value on that sensor can have a small effect on your measurement because there are leakage currents coming out of your amplifier. Bottom line is, if you have about, rough numbers, if you have a 10K ohm pot, then the source impedance is about 2,500 ohms. Most amplifiers today have very, very low leakage. It's nanoamps range, and that doesn't cause a major effect. If you're a 1,000 ohm pot, the source impedance works out to be about 250 ohms. And of course, an ideal source impedance should be around 100 ohms or less, between 100 ohms and 0 ohms. So you want your pots for position to be around 1,000 ohms, 2,000 ohms. Definitely less than 10K ohms is just some guidance. Your measurement off of that pot is going to be a percentage of excitation. So as that wiper arm goes up and down, it's like a voltage divider. You're getting a pickup. You're reading the voltage out as a percent of travel across the whole potentiometer. A 3-wire measurement is immune to operating temperature changes on the sensor. So if you have a stable excitation source of 0.3 volts, and your resistance happens to change, let's say your wiper arm is in the middle reading 50%, so you're reading 0.15 volts out, and your resistance changes from 1K ohms to 990 ohms or up to 1,100 ohms, it's still going to be reading 50% because you're making a 3-wire measurement and your 0.3 volts is not moving. So the sensor is immune to operating temperature changes. That's a good measurement for position or level. Now, you can just wire up across 2 leads, the wiper arm in one end, and that's actually called a rheostat. That's more of a true resistance measurement, not a voltage divider. And Acromag's amplifiers will also do that. But if you're just doing a 2-wire measurement off of a pot or slide wire for position or level, now you have 2 problems. One, the resistance in the lead wires is going to be combined with the sensor resistance, so it's going to affect your reading a little bit. To whatever the lead wire resistance is, that will be your error. Secondly, if the resistance changes over temperature, in other words, you're operating the ambient temperature changes over the sensor, and the rheostat resistance changes, it's going to affect your reading. So 2-wire sensors are considered good, especially if you have short lead wires and things are closely coupled with the amplifier. But your best measurement technique on a pot for position or level would be a 3-wire measurement. Let's see, moving on. Acromag's newest product solutions. for potentiometer measurements. Up in the upper left-hand corner is the new TT234-0600. This is a 12.5 millimeter wide line of USB configurable signal conditioning. It offers a 4 to 20 milliamp output that can be wired as a sinking output or a sourced output. Very unique in the market. Its operating ambient temperature on the amplifier is minus 40 to 80 C, and it's designed to be located in Class 1 Division 2 areas. Down at the bottom, we've got the TT334-0700, very similar product, a little bit wider at 17.5 millimeters wide. But if you need a universal voltage or current output, specifically plus minus 10 volts, plus minus 20 milliamps, or 4 to 20 milliamps sourced or scaled anywhere in between, the TT334 will do that. It operates over the same ambient temperature and also designed for Class 1 Division 2 areas. It even has a redundant power feature on there if you're looking for redundant power on your amplifier. Now, over to the right is a copy of the USB software page that you would configure your potentiometer interface for. It's very simple. Up at the top, hopefully you can see that. It says input type. You're going to select potentiometer Slidewire. There's a pull-down menu for filtering. You can have none, low, medium, or high, and that'll give you variable response time on this. I think down as low as somewhere around 20 milliseconds. 11 to 20 milliseconds is no filtering, and the highest filtering is close to a second. Okay, and when you scale your pot Slidewire transmitter, it's in terms of percent. You're going to just, for example, if you want, when the wiper arm's at one end, it's 0%. When it's at the other end, it'll be 100% input. You want that to equal 4 to 20 out. You just put your scaling in terms of percent. Some people might want to scale their pot like 10% in to 90% in equals 4 to 20 out. You can do that too just by changing your scaling. So that's how easy it is to configure a pot Slidewire amplifier. Okay, let's see. Moving on. This section talks about thermistor sensors. Okay, what are they? Well, the term thermistor is a combination of two words. It really means thermal resistor. And it's a variable resistance sensor, and it's actually a piece of silicon or semiconductor, and it varies in resistance to temperature. And this type of sensor is used to monitor low temperature ranges, typically minus 90 to 130 degrees C. In actuality, I've seen thermistors used for like 0 to 100 degrees C measurements, 0 to 50 degrees C, or maybe minus 25 to 50 degrees C. Very narrow span, kind of even ambient temperature ranges for thermistors. They give you high resolution. In other words, they give you a high number of ohms per degree C output. So people like these for very narrow ranges because they give you a high resolution output. It's a two-wire connection off of the sensor, and they're also considered fast response sensors. Typically in the tens or hundreds of milliseconds range, these sensors can respond. There's two basic types. There are sensors called PTC. They've got a positive temperature coefficient output, meaning as temperature increases, the resistance increases. Then there's an NTC type, negative temperature coefficient. That's the opposite. As temperature increases, the resistance decreases and approaches 0 ohms. Little history, who invented the sensor? It was discovered in 1833 by Michael Faraday when he was working with silver sulfide behavior. He just noticed the variable resistance over temperature. However, he didn't really make a production or commercial sensor. That didn't really come out until about 1930 when Samuel Rubin invented or perfected a production sensor that could be used in industry. Okay, some thermistor applications. Well, PTCs are typically used as current limiters or fuses in circuits. They tend to have a kind of a stable resistance output, and then as temperature increases, and then when they hit a certain temperature, then their resistance goes to infinity, and they're used as current limiters or fuses, sometimes even self-resettable fuses. They're also used as part of degaussing circuits in old CRTs. They also can be used as heaters. Now, negative temperature coefficients are probably more popular. They're also used as inrush current limiters for power supplies, but the most dominant application for thermistors is for temperature monitoring. That's what we're going to focus on here today. Negative temperature coefficient thermistors are used for temperature monitoring in digital thermometers. They're used in environmental chambers like incubators, printers, batteries, We've seen them used in automotive, coolant and oil as temperature sensors, manifold temperature sensors. We know they're used in the food industry and processing equipment and a lot of consumer appliances. I'm showing you their toasters, coffee makers, freezers, dryers. They're used all over the place. Some of the pictures over to the right here, there's a greenhouse image, and in a greenhouse or environmentally controlled chamber, you've got a room temperature sensor, you've got an outside ambient temperature sensor, you've got an earth temperature sensor, there might even be humidity. A lot of solar applications have weather stations tied to their, into their system, and they're either using, I'd say, thermistors in their weather stations or RTDs. Okay. Down below is just an illustration that thermistors can be used as part of current control circuits. So we do see thermistors being used as part of electrical circuits as well. They could even be used as cold junction compensation sensors on a thermocouple amplifier circuit. Okay, bear with me. Thermistor construction, well, PTCs are kind of, known as a doped polycrystalline ceramic material. Specifically, a barium titanate is the type of material that PTCs are used on or constructed from. Also, PTCs might be plastic with carbon grains embedded. And the way that works is, as the plastic heats up and expands, the carbon grains spread out and the resistance goes up. And as temperature decreases, the plastic contracts and the carbon grains compact, and you get less resistance. So that's kind of how that works. A little bit of history is W. Haywang and G.H. Jonker modeled this behavior of PTCs in the 1960s. Now, NTCs are more of a semiconductor material. They're usually a pressed disc or a cast chip of a semiconductor, such as maybe a sintered metal oxide. Okay, and there's two gentlemen, Steinhardt-Hart, that actually developed an equation based on different materials, semiconductor materials, where it's shown there, where T is in temperature in kelvins, R is a resistance, and the ABC coefficients are the Steinhardt-Hart parameters for that particular semiconductor material. Okay. Over to the right is a nice graphic of how they're constructed. You can see it's basically semiconductor material with probes embedded inside, and this is a multi-probe construction. And this little table sort of tells you why a multi-layer, multi-probe construction is better than a single probe. It gives you excellent performance for controlling the resistance, for high frequency range and other factors. So that's a good graphic on there. And down below, they're showing you actually is a nice graphic on how simple a thermistor, it's almost like an RTD. You've got your thermistor semiconductor sensor kind of encapsulated inside of a sheath. You've got insulated wires and insulation materials and two wires coming out. Let's see where we're at here. Next page. This is a great graphic. It says temperature sensor comparisons. The source was from Agilent Technologies. I thought it was great. It kind of gives you advantages and disadvantages between thermocouples, RTDs, thermistors, and even IC sensors. Now today we're only focusing on thermistors and RTDs, but I know a lot of you probably use thermocouples. We'll probably have a whole separate thermocouple webinar in the future. But this is a great table, starting with thermistors' advantages. They have a high output, or considered a high signal output. They're considered fast, and they're two-wire measurements. In other words, you don't have to worry about lead wire compensation typically. The downside to thermistors is that they're highly nonlinear, and trying to find a good amplifier to amplify your thermistor sensor is going to be difficult off the shelf. They're out there, and Acromag has a terrific one, but they're hard to find, which means a lot of OEMs that use thermistors have to create their own circuit to interface to them. They've got a narrow temperature range. Like I said earlier, they're typically within 0 to 100 degrees C. They can be considered fragile in a heavy shock and vibration environment. You need a good voltage or current source to excite them, and they can be susceptible to self-heating if you don't watch the amplifier. Remember, it's a semiconductor type material. The other downside to a thermistor is that if you run them too hot, way over their design range or near the end of their limits, they can actually get out of calibration. You can hurt the sensor. Now we're going to be talking about RTDs in the next section, but just to quickly go over it, because I'll go over it faster later, the same slide. RTDs are considered more stable, more accurate. They're nonlinear, but they're definitely not as nonlinear as a thermistor. They've got a slight bend of the curve, as you can see in the graph, and they're easier to I would say, build a circuit for than a thermocouple. So the amplifiers are usually, they might cost a little less. The downside is the sensor itself might cost a little bit more. I wouldn't say they're expensive, but they might just cost a little bit more than a traditional thermistor or even a thermocouple. They can be slow because there's a thermal mass to the RTD that you'll learn about later. They're encapsulated. They're slow responding devices. They usually take 1 second up to 10 seconds to actually change to the steady state. So their response time is in seconds. They also need multiple wires for lead wire compensation when you wire to them. Now thermocouples, which we're not really talking about, but I'll go over the slide, they're self-powered devices. They are simple and rugged. They're low cost, and they go up very, very high in temperature, thousands of degrees Celsius or Fahrenheit. They're nonlinear. They are low voltage, so if they're in a very noisy environment, you're talking millivolts or microvolt output, and they might be more susceptible to large noise in some applications. But they're widely used, especially if we're going very, very cold and very, very hot in applications. All right, measurement techniques on thermistors. The top diagram is a good graphic on how you would excite and measure a thermistor. It's actually put in part, it's installed inside of a voltage divider circuit where you need a good excitation source. The thermistor is typically the bottom leg, and the top leg is a fixed resistance like 10K ohms. It is a two-wire sensor. Typically we're talking about NTC type thermistors that are being used for temperature measurement. Again, it's a voltage divider measurement. You can see down below, Acromag strategy uses a very precise 1.25 volt excitation, very stable. There's a 10K ohm top leg resistor, and in the bottom is a thermistor, and that's that variable resistance, which will typically vary, like if it's a 3K ohm thermistor over 0 to 150 degrees C, that resistance will vary roughly 10K ohms down to 0. And if you're using that thermistor in a minus 40 to 150 C, that resistance will vary from 100K ohms down to 0. Again, most people are using thermistors for like 0 to 50 C or minus 25 to 75 C. Now, if you've got 5 to 10K ohm thermistors, and I'm not showing you all the tables right now, but the resistance will vary from 30K to 0 ohms or 240K to 0 ohms. And you can see, just by looking at these ohms over the narrow range, that's a lot of ohms per degree C output. So that's why people do like thermistors, is you got great resolution per degree C of output. Okay. Now, keep in mind, when you've got these sensors, you need a good amplifier because the sensor is nonlinear, and it's actually a negative temperature coefficient. So if you want to get an output like a 4 to 20 milliamp to temperature, you need something with good linearization on board to temperature. And you don't have to worry about lead wire resistance. It's just a two-wire measurement, any gauge wire. Okay, moving on. This screen looks similar to the one I showed you earlier. We used the same two models, the TT234, the TT334. It's the same amplifier, just picking a different input type as our potentiometer slide wire. The screen over to the right says under input type, you see thermistor. It says use the thermistor table. I'll show you that on the next screen. The input filtering is adjustable from about 11 milliseconds up to 1 second. With the temperature sensor, though, you get a choice to select break detection. So if that sensor breaks open, you can program the output on the amplifier to go over range or under range, upscale or downscale break. And here, when you scale the unit, notice with the thermistor, we do all the linearization for you. You're going to scale it in terms of degrees C, degrees Fahrenheit, or even Kelvin. So it's doing all the linearization for you. Okay. This next screen, if you click on that thermistor table, you will see, for example, to the left here, a 10K ohm thermistor. Here's the table for it, and the customers are able to change that table if they want, but there's a lot of preset standard thermistors in this pull-down menu. Over to the right, you can see there's a 2.252K ohm thermistor, 2.795, And thermistors are usually referenced as their R25 resistance. That means the resistance at 25 degrees C, for example, might be 10K, or it might be 2,252 ohms. They also have a beta value, and that's taking the resistance at 25 divided by the resistance at 85 degrees C, and they give you that beta value, and it's 3978. So if you're using a thermistor, and you want to know if you've got the right amplifier, you want to key into the R25 value of your thermistor and the beta value. Okay. The other neat thing Acromag's doing here for you, if you're using thermistors, you can select custom user table, or down below you can select use Steinhart coefficient table, and I've showed you a screen at the bottom where if you've got a material and you've got the coefficients, we'll do the math. And you just put those coefficients in there, and see, since thermistors can be semiconductor material, there's a lot of standards out there, but there's probably a lot of proprietary sensors too if you're an OEM, and this amplifier will take care of all that for you. This just happens to be a graph. If you were to hit display graph, you will see, resistance on the y-axis and degrees Celsius on the x-axis across the top. And this, if you are buying a sensor and the data sheet has a curve, this curve displayed here ought to line up with the curve on your sensor data sheet. Okay, now we're going to talk about RTDs. RTD stands for Resistance Temperature Detector. What are they? They are also variable resistance sensors. They are also used for temperature measurement. They work on the phenomenon that all base metals have a temperature coefficient. They will vary in resistance over temperature. Now, there's three basic sensor types with RTDs. You've got platinum, and of all the platinum RTD sensors, 100 ohm platinum with a 385 curve is the most standard that's used worldwide. However, there's a lot of legacy type platinum sensors out there. There's 200 ohm platinum, 500 ohm, even 1,000 ohm platinum. Now, there's also a lot of 10 ohm copper sensors out there, and also some 120 ohm nickel. Acromag runs into mostly 100 ohm platinum, 385, 10 ohm copper, and then after that, we do see some 200 ohm, 500 ohm, 1,000 ohm platinum sensors being used. Frankly, they're being used to try and perform like a thermistor does, because they kind of give you more signal output. But there you go. A little history. Who invented the sensor? Well, Werner von Siemens invented a platinum RTD sensor in 1871, but in his unit, it wasn't very good with shock and vibration. It wasn't very good for practical applications. In about 1885 to 1890, gentleman Hugh Longboard Callender came, and he actually produced a commercial grade unit. It was with his manufacturing, and it was much more robust for as a commercial sensor. And then in about 1925, there was another gentleman, Van Dusen is his last name. He worked for NIST. He actually simply expanded the table for RTDs, 100 ohm platinum, down to minus 200 degrees C, I believe. So for many years, you'll see RTD tables for platinum referencing the Callender Van Dusen tables. That's a little bit of history. Over to the right are some RTD sensors. They come in all different shapes and sizes. There's a field mount temperature transmitter where way over to the right where the sensor's on the bottom. In the top is either a junction, a terminal where you would land wires, or a transmitter that would convert to 4 to 20 milliamps. In the middle is an idea, or not an idea, an illustration of how an RTD sensor might be constructed. They're kind of showing you where the spot welds are and maybe nickel wire material. And down below, this was a table I thought was useful. Just to give you an idea, the temperature coefficients of common RTDs, platinum might be like 0.0039 ohms per ohm per degree C, and that can vary. Like I was saying earlier, the most popular is a 100 ohm platinum that varies roughly 0.385 ohms per degree C. You'll see in this table there's copper and there's nickel and some other materials. Okay. Moving on, how are they used? These are used for what I would call for precision temperature measurements. People that can tolerate some response time. They don't want their temperature measurement jumping around. They want it to be more stable, more accurate. And again, they can tolerate a second or two on this thermal lag when the temperature actually changes. RTDs can touch a material, but more importantly, they're encapsulated sensors. They go into a thermal well, and they're used for a lot of non-contact that kind of get immersed into a process, but they're not really touching it. Typical range for RTDs is from -200 to 500 degrees C, although we see RTDs typically used in the -50 degrees C to maybe 200, 250 degrees C range, almost half of that wide dynamic range. If you need to go beyond that, we see people using more thermocouples for their temperature sensors. These are used in heaters, liquids, air ducts, airflow, motor control centers. 10 ohm, I can tell you there's 10 ohm copper and 100 ohm platinum. RTDs are used in motor windings and also to sense bearing temperatures. They're used in the HVAC industry and environmental controls, and also sanitary, pharmaceutical, food, dairy, beverage. They're used all over the place, as the poll that you filled out earlier showed. They are an alternative to thermocouples and thermistors. The construction, there's three basic types. There's thin film, shown here, then there's wire wound, and then there's coiled. Now, thin film is usually a platinum material on a ceramic substrate coated with epoxy or glass. They're not very good for shock and vibration or wide temperature fluctuations because of the strain that happens could change the value. But they are good sensors for narrow ranges, and they have their place. Wire wound is probably one of the most popular, or has been over the years, where they coil wire over an insulator and then encapsulate it, and then they match up the lead wires to the platinum material, for example. And wire wound has been used for many years. It gives you good performance over a wider temperature range and not as susceptible to strain. The best that has been replacing wire wound RTDs is this coiled construction. Coiled, as you can see in the picture, uses coils. They're put inside of a kind of a ceramic oxide tube that has bored holes in it. This gives you the best performance over temperature, the maximum strain relief. You don't get stresses or strains. So a lot of RTD sensors that are out there are using this coil type. There's other types of RTDs that use carbon or strain-free, but those are the most popular, and of those, coil seems to be taking over. When you make an RTD temperature measurement, you can wire up to it with 2 wires, 3 wires, or 4 wires. The picture that was picked here is actually showing only 2 wires coming off of the sensor, but in actuality, at some point in that sheet, there's up to 4 wires that come off of that sensor, so that when you connect to it, you can connect to either 2, 3, or 4 wires. There's usually another wire coming off of the top lead connected to it, and another wire coming off of the bottom lead. Okay, moving on. You've already seen this graphic. I just put it here so when you download the presentation later, it'll be in this spot. I won't take time to go through this. Measurement techniques. Already covered this, but when you measure an RTD, you got to make a choice: 2-wire, 3-wire, or 4-wire. 2-wire connections actually give you the poor temperature measurement, because the lead wire resistance now becomes part of the RTD sensor measurement. So you get no lead wire compensation. If your lead wires change over temperature, that gets additive to the RTD resistance, and it becomes error. However, if you keep your lead wires very short, keep your amplifier right next to the RTD sensor, then it really doesn't matter. Like if it's in a field mount temperature sensor, and it could even be considered fail-safe, because you only have 2 wires going out to the RTD. If they break open or shorted, they're going to go into a break detection mode, and it can actually be considered fail-safe in some applications. 3-wire connections are the most popular. They allow you to put your amplifier at a good distance away from the sensors, hundreds of feet. I've seen people even go thousands of feet away. So 3 wires going out to the sensor gives you what's called lead wire compensation based on that 3rd wire. The only caveat to using a 3-wire measurement is you want all the lead wires typically balanced, roughly the same number of ohms per leg in each lead wire. Any error or an imbalance in those lead wires can show up as error with your 3-wire measurement. Typically, when you have amplifiers, they don't want you to have more than 10 ohms per leg with a 3-wire measurement. Definitely the most popular. We see this on PLCs. We see this as being the most popular with signal conditioners and network I/O devices. You don't have to run that 4th wire. It gives you great performance. It's the most popular. Now, if you're really looking at the best, a 4-wire connection is called a Kelvin connection. That's where you have 2 wires going all the way out to the RTD, bringing current and excitation directly across the RTD. Then you have 2 wires also coming back from reading across the RTD that are just sense lines. There's no current in those lines. So effectively, you got 2 wires to excite the RTD and 2 wires just to sense directly across it. That gives you the best measurement. Lead wire, it gives you lead wire compensation, and the resistance in any of the wires does not matter. So if you're in a laboratory environment or you're looking for the best 4-wire measurement, is what you want to do, and you want to look for that in your amplifier. So Acromag has 2 new products. The TT235 up at the top is Acromag's new RTD temperature transmitter. It's USB configurable. It gives you, just by wiring up to it, a 4 to 20 milliamp out sinker source, wide operating ambient, and designed for Class 1 Div 2 environments, hazardous locations. The TT335, same thing, but it gives you, that universal voltage or current output if you need voltage. The screen over to the right shows you how easy it is to configure your RTD amplifier. While I did not click on the pull down, if you click on the pull down for input type, you're going to see a whole list of different platinum RTDs, 100 ohm, 200 ohm, 500 ohm, with different alphas, 385, 391, 392. You just select what you're using. Again, the most popular and the default is 100 ohm platinum 385. You get to pick your number of wires for configuration. Another number of wires you're going to be using to wire up to the sensor. That's going to be 2, 3, or 4 wire. And you also get to pick the filtering, the response time of the amplifier, none, low, medium, or high. Okay, very easy to configure these. You select your temperature in units, Celsius, Fahrenheit, and Kelvin, and you're going to scale the unit in terms of temperature because we do the linearization. So you're just going to put in, for example, 0 to 100 degrees CN equals 4 to 20 milliamp out. You're going to download that into the module. It really couldn't be easier. Okay. Now this next page, we're getting near to the end of the presentation. We've talked about the signal conditioners, the TT230. I just wanted to show you, especially if you're in the process market, how easy it is if you need a 4 to 20 milliamp output now in your process. You're just going to look for the TT230 product. And I wanted to show you in the picture on the bottom, if you just wire up across terminals 6 and 5, you get a true 2-wire loop-powered measurement to your DCS or your PLC input card, okay? If your input card does not have 24 volts on it, and you've got a local 24-volt supply, you wire up your supply to terminals 6 and 7, and then you get your source 4 to 20 milliamp output off of terminals 5 and 8 as shown. So again, you don't even select this with the software. You just wire up to it the way you want, and it'll give you a sinker source output. Very easy. It makes it almost impossible to not specify the right 4 to 20 milliamp output amplifier. Okay, the TT330. Here's an output schematic up at the top across 9 and 8. If you just want a source current output, and again, that could be 4 to 20, plus minus 20 milliamps, or anywhere in between. Or if you want a voltage output, plus minus 10 volts, plus minus 5, 0 to 5, 0 to 10, or anywhere in between, you just wire up across 9 and 8. We wanted to point out that across 11 and 12 is where you would land your separate power, or you could also power down at the rail, or both. Local power on 12 and 11 and down at the rail. They're diode coupled. This will give you a redundant power strategy to the unit. So if you lose power in one power supply, the other one kicks in seamlessly. The TT330s are known as a 4-wire device. The TT230s are known as 2-wire and 3-wire devices. Okay, so in summary, thank you for sticking with me. In summary, we talked about potentiometers and slide wires, the fact that they're position or level sensors, they're fixed resistors are typically used in a linear output mode, and for position or level, you really want to connect up to them using 3 wires and as a voltage divider output. You can use them in some circuits as a rheostat. That's just a 2-wire measurement. You might have that going on. They're used for manual control and adjust. Yeah, the 3-wire connection is your best, and you want to keep your pots around 1,000 ohms or 2,000 ohms, or definitely less than 10 k ohms to keep your source impedance down. If you're using thermistors for temperature measurements, we discussed that NTCs are the most popular. They're just a 2-wire measurement. They're good for narrow ranges, 0 to 100 C or within. They can be low cost. They can be fast acting, 10 or hundreds of milliseconds, but they are nonlinear. So watch the amplifier that you're buying. Acromag has some great ones on the market. Your RTD transmitters, We discussed that 100 ohm platinum 385 curves are the most popular, but there's others, 10 ohm copper, 200, 500 ohm, 1000 ohm, even 120 ohm nickel. They're good for wider temperature ranges than thermistors, approaching minus 200 to 500 degrees C range. They can be slower response time because they're encapsulated and have a thermal lag. As your process temperature changes, it might take a second or two for the RTD to heat up. They're considered higher accuracy and more stable. In other words, you don't see things jumping around in your amplifier because they do heat up a little slower. Okay, well, I'd like to thank you very much. For more information, you can go to Acromag's website at www.acromag.com/TT. That'll give you more information on Acromag's new TT series. There's our group phone number here based in Michigan in the USA, and our group email is sales@acromag.com. You can actually, that's sales@acromag.com, just so everybody knows, you can send any technical question, you can send orders there, or just hit our group with any question you have, and it's being monitored daily, and you'll get fast response with that email. I'd really like to thank you for sticking with us today. We hope you found this useful. Feel free to send us an email, give us some feedback, let us know what you thought.